Salut tout le monde. Welcome back to another differential geometry reading stream. This is episode 28. I'm Anthony, obviously, and we've been reading from none other than Differential Geometry by Erwin Kreisig, rest in peace. And we are currently in chapter 6 on mappings, but this chapter might as well just be called conformal mappings. But we are in section 68, conformal mapping of the Euclidean space, which starts in the Dover edition on page 212. And this is actually the last section of this chapter before we get to chapter 7 on absolute differentiation and parallel displacement, which from the first paragraph of forthcoming chapter 7, that was like one of the first things I read in this book when I got it now, like over 10 years ago. And back then I was just getting my undergrad in math, and honestly I never got around, never had the intellectual discipline, intellectual maturity, the free time in order to get into this book, to appreciate it, to give it the attention it deserves, going from the very beginning all the way to chapter 7, section 69. Okay, we're about to get to that after this episode, which, like I said, is on conformal mapping of the Euclidean space. But first, this is one of my favorite segments of this series, which is reading comments from viewers like you. So if you would like one of your comments to be featured in a future episode, comment down below. And I actually was making a video just now, which is a standalone outside of this differential geometry reading series, which is responding to a question where I got basically like a challenge problem from abstract algebra. And I was like, this is a series about differential geometry, but I'm going to do it anyways. I'm doing it for the people. I'm doing it for you guys. So that's probably already out. I'm a little bit behind on my editing and stuff, but that's probably a good thing. It's probably good for me to be ahead filming, and that way I have a more consistent upload for you guys, because with these videos being really long, the editing can take up like all weekend. And so if I don't finish on Sunday editing the video, that's why then it uploads later in the week, is because then I'm spending after work a few hours here and there to finish up the edit anyways. But it's definitely better for the analytics if I schedule it to upload like first thing 8 a.m. Monday morning. But this week we've got some OG comments from the one, the only Vanderhagen, the Stampede, whose name is a funny story but is a myth. But we're not going to ask, because we're not going to intrude on people's personal lives, and it doesn't matter if you guys don't have real names or profile pictures. I'm still going to keep it engaged. Vanderhagen the Stampede writes, an example of how our current understanding of fundamental physics can be incomplete or inconsistent is the Abraham-Minkowski controversy. This is interesting because, immediately I'm thinking Minkowski cone, which revolves around the correct expression for the momentum of electromagnetic radiation in a medium. Specifically, Abraham's suggestion is that the momentum of light should increase as its velocity decreases when it passes through a material. This implies that light behaves like a classical object with mass. On the other hand, Minkowski's prediction is that the momentum of light remains constant regardless of its velocity in a material. This perspective is consistent with the behavior of a massless particle, a photon. In other words, the controversy centers on how much of the momentum should be attributed to the material and how much to the electromagnetic field. This affects our comprehension of energy momentum conservation. If Minkowski's perspective is correct, it could lead to the possibility of reactionless drives that produce motion without expelling a propellant. This is Elon Musk's dream, of course. However, a recent satellite testing program failed to deploy an experimental propulsion system. Remember the frenzy surrounding EM drive? I do not, but I am a little bit familiar with what that is, due to ongoing power system issues. Yeah, there are definitely some frontiers of propulsion science books that I'm trying to get my hands on and read about that stuff. It's just like, really interesting, but like you said, something like a power system issue comes up and just reminds us of the materiality of the universe that, people are up against when, you just think of these things. And then when you actually set out to build the technology, implement them in the real world, as they say, that's what the job's all about. And then we have another comment. Sabine Hassenfelder video, quantum inertia drive put to the test. It didn't go as planned. Everybody loves some good old Sabine Hassenfelder videos, you know what I'm saying? I love these Vanderhagen the Stampede comments, though, because it keeps the physics theme going with these videos and ties in these concepts, however tangential it may be, but it keeps it on that same sort of theme. Moving on, we're getting to learn more about the man, the myth, the legend. I'm exploring Mike McCulloch's quantized inertia theory in the hopes that it may hint at a higher framework for relativity and quantum theory. This is really interesting. I'd love to hear more about this. McCulloch suggests that inertia is not an inherent property of matter itself, but rather a result of the interactions between matter and the surrounding quantum vacuum. I'm not wearing a tinfoil hat, though. I'm not expecting faster than light travel or even Jetson-esque flying cars. Yes, definitely last video's probably not getting boosted by the algorithm, so true flop probably. I don't care. I don't really care about views. I just really want to complete this series, really, and then give you guys an ultimate supercut math audiobook of differential geometry, Erwin Kreisig. So subscribe if you are looking forward to that. When I'm done reading this entire video, I'm going to cut out all these intros, cut out all these rants, and give you just the straight up me reading supercut beginning to end of this book. But never heard of Mike McCulloch's quantized inertia theory. Definitely look into that. But, speaking of tinfoil hats, yeah, there are themes of this series where I touch on some of that, like conspiratorial alien UAP, NHI, interdimensional stuff. And it's not a tinfoil hat that you would need. You would need like a Faraday hood that completely covers your face. It would look almost like what people wear when they're getting like these advanced, essentially the radiotactic surgeries. Because like if you're wearing a Faraday cage as a sort of a hood and you don't have your face covered, you could still be getting blasted by stuff in your face. And like, but yeah, tinfoil hat, just erasing the stigma around, oh, if you look into alternatives to mainstream general relativity, gravity, you're a tinfoil hat, whatever, Men in Black guy. That, I feel like, is getting phased out. But let me put it to you in another way. A conspiratorial take on modern theoretical physics would be that Ed Witten's string theory is just mathematical art. Saying that would get you in trouble in a university, probably. But the way I see it is, even if it is art, it still is important to consume art, contemplate it, take it seriously, if you will, because I think Immanuel Kant once said, in addition to things like serious critique of pure reason, you could say today, nobody since Kant has said it better than he has. You can throw away Hegel, everybody after Kant, because Kant and his strict critical reasoning, that's as good as it gets. Even Immanuel Kant, in his time, he would tutor like German princesses and be writing about things like aesthetic beauty, but in the Immanuel Kant super serious philosophical way. And Kant said that art is important because it helps keep the wayward aspects of ourselves in check. And so if Ed Witten's string theory is not the end-all be-all, blah, 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 and it is just mathematical art, it still is worthwhile to learn about that, get on his level and all that stuff. So thinking about these things, higher frameworks for relativity and quantum theory, is worthwhile. If you're not just working under some professor to get the low-hanging fruit, developing the frameworks that they already came up with, that they were already inspired by some other professor before them, and so on and so forth. You want to work on the, running out into the deep blue waters and make your own footprints on the fresh fields of snow. Let's do it, bro. So on that note, let's finish up reading chapter 6, Conformal Mappings from Differential Geometry by Erwin Kreisig. We are in section 68, Conformal Mapping of the Euclidean Space. We consider the Euclidean space R3 and assume that Cartesian coordinates have been introduced in this space. Let y sub I equal the function h sub I entry-wise x1, x2, x3, where I can be 1, 2, or 3 respectively, be functions of class r greater than or equal to 1, which as we know means that they are at least 1 times differentiable, and that out of all of them, these components' derivatives do not all go away to 0, which are defined in one and the same domain, capital B of R3, whose Jacobian is different from 0 everywhere in said domain B. By means of these yi equal to functions hi to any point P of this domain B with the position vector x, entry-wise x1, x2, x3, there's associated a point P star with position vector y equal entry-wise to y1, y2, and y3. The domain B is thus mapped onto a certain domain B star of R3. If in particular B and B star are both identical with the entire space, the mapping is called a mapping of R3 onto itself. A one-to-one mapping of class R which maps the domain B of R3 onto a domain B star of the same space is called angle-preserving or conformal, as we have already defined, if for any pair of intersecting curves the angle of intersection of the images is equal to that of the corresponding inverse images at the corresponding point. So we're just getting a little bit different of a definition than from a few sections ago. We shall restrict our consideration to conformal mappings for which the image of any surface of class r greater than or equal to 3 is of class r star greater than or equal to 3. Such a mapping will be called admissible. Conformal mapping of Euclidean space differs from that of the plane in many aspects. For the plane, there does not exist a theorem analogous to the theorem 68.2 of Louisville, which is coming up in a few pages. The image of a circle in the plane, when being mapped conformally, is not a circle in general. While in the plane, any regular function f of z gives rise to a conformal mapping, for which referred to the previous section 64, we shall find that there are very few types of conformal mappings of space. It will be proved that any admissible conformal mapping of Euclidean space can be decomposed into inversions, which we will see in theorem 68.3 coming up soon. This means that inversions, that is, mappings of the form vector y equals r squared times a fraction vector x over a denominator x scalar product with x, are the only non-trivial admissible conformal mappings of the space. We will first consider some properties of those mappings. Without great loss of generality, we may set r equal to 1, that is, we consider the mapping vector y is equal to vector x over the scalar product of vector x with itself, where, of course, the vector x cannot be 0. The transformation is called involutory if two successive applications of it result in the identity transformation. Inversion is involutory since when the aforementioned mapping denoted by the vector y above, and then another inversion, vector z equal to vector y over the scalar product of y with y, are applied, we obtain that the vector z is equal to, as previously mentioned, vector y over y scalar product with y, which is then equal to fraction where the numerator is the vector x over the scalar product of x with itself, then times another fraction where in the numerator we have the square of the scalar product of x with itself all over then just the scalar product of x with itself. This is all equal to then the vector x. So since in the mapping denoted by the vector y, The denominator, which is the scalar product of x with itself, is a positive scalar. A point in space and its image lie on the same ray of a single straight line passing through the origin O of the coordinate system. Furthermore, from this mapping denoted by the vector y, if we have the scalar product of y with itself, then we get 1 over the scalar product of x with itself. That is, the product of the distances from the origin of an arbitrary point and of its image is always equal to 1. The fixed points of the transformation denoted by the vector y can be obtained from the condition vector y equal to vector x, that is, from vector x equal to vector x over the scalar product of x with itself, or the scalar product of x with itself is equal to the magnitude squared of the vector x, which is then equal to 1. Consequently, the image point of any point P on the unit sphere with the center at the origin coincides with that point P. The inversion is therefore also known as a reflection in a sphere of radius r, in our case r equals 1. And we actually saw a little bit of this in an earlier episode on conformal mappings, where I opened up the visual complex analysis book and we looked at complex inversions with respect to the unit sphere briefly, and we already saw in that how we have the result that inversion, complex inversion, that is conformal. And if I'm not mistaken, yeah, that is coming up on this page. So the origin O of the coordinate system is called the pole of the inversion. It has no image point, but if we close the space at infinity by just one point, capital Q, then the origin and Q correspond to each other, and the inversion becomes a one-to-one mapping in the whole space. So we got a nice point at infinity there. A sphere through the origin inverts into a plane, its points being transformed according to stereographic projection, which is previous 2 episodes ago or something like that now. Other spheres invert into spheres. Straight lines and planes may conveniently be regarded as circles and spheres through the point at infinity, Q, as we just said. Indeed, let A naught then times the scalar product of x with itself plus the sum on the index I from 1 to 3 of a sub I times x sub I plus a sub 4 is equal to 0. Let that be a representation of a sphere. Then we obtain from our mapping denoted previously by the vector y that we have a sub 0 or a naught plus the sum on the index I from 1 to 3 of a sub I times y sub I plus a sub 4, then times the scalar product of the vector y with itself is then equal to 0. Inversion is conformal, and this can be proved as follows. Let the vector x in terms of s, presumably arc length, and vector x over bar in terms of sigma be any two intersecting curves, and vector y in terms of s star and vector y over bar in terms of sigma star be the respective images. Like I just presumed, s sigma, s star, and sigma star denote arc lengths. Then the derivatives, vector x sub s, vector x over bar sub sigma, vector y sub s star, and vector y over bar sub sigma star are all unit vectors. Hence, the angles of intersection of the curves and their images are equal if the scalar product of vector x sub s with vector x over bar sub sigma is equal to the scalar product of the vector y sub s star with the vector y over bar sub sigma star. And we will prove this statement. So from our y vector mapping from previously, we have that the vector y sub s star is equal to vector y sub s then times ds star, which is equal to a fraction where in the numerator we have the vector x sub s then times the scalar product of x with itself, then minus the vector x times the scalar product of 2 times the vector x with the vector x sub s. And this is all over a denominator of the square of the scalar product of the vector x with itself. Then that fraction is all times ds star. So since the scalar product of xs star with itself is equal to 1, and similarly the scalar product of the vector y sub s star with itself is equal to 1, we obtain from the expression for the vector y sub s star, which we just expressed previously, we have that ds star is equal to the scalar product of x with itself. Analogously, we have that the vector y over bar sub sigma star is equal to a fraction with the numerator, vector x over bar sub sigma, then times the scalar product of the vector x over bar with itself, then minus the vector x over bar times the scalar product of 2 times the vector x over bar with x over bar sub sigma, all over a denominator of x over bar scalar product with itself. By taking the scalar product of these relations for vector y sub s star and the vector y over bar sub sigma star, and using the fact that x over bar is equal to x at the point of intersection, we obtain the relation scalar product of xs with x over bar sub sigma equals vector y sub s star scalar product with y over bar sub sigma star. We now explain the concept of curvilinear coordinates in space. These coordinates resemble curvilinear coordinates in a plane, such as polar coordinates. Curvilinear coordinates u1, u2, and u3 can be introduced by a transformation of the form x sub I equals function h sub I in terms of u1, u2, and u3, where I can be 1, 2, or 3 respectively. We assume that the functions h sub I are defined in the whole space and are of class r greater than or equal to 1. Furthermore, the Jacobian of these is given by capital D equal to partial in terms of x1, x2, and x3, partial in terms of u1, u2, and u3, which is equivalent to this determinant where column-wise we have partial h1, partial u1, partial h2, partial u1, partial h3, partial u1, and then in the next column, partial h1, partial u2, partial h2, partial u2, partial h3, partial u2, then in the next column, partial h1, partial u3, partial h2, partial u3, partial h3, partial u3, and this Jacobian is assumed to be not identically 0. Then, in a neighborhood of every point at which this Jacobian is non-zero, there exists the inverse transformation denoted u superscript 1 equals a function u in terms of x1, x2, and x3. We have curvilinear coordinate u superscript 2, which is equal to the function v in terms of x1, x2, and x3, and then we have the curvilinear coordinate u3, which is given by the function w in terms of x1, x2, and x3. The surfaces where u1 equal to u equal to a constant, u2 equal to v equal to a constant, and u3 equal to w equal to a constant, these surfaces are called coordinate surfaces of the u1, u2, u3 coordinate system. These surfaces constitute a system of 3 families of first order infinity surfaces. Infinity 1 surfaces, not exactly sure on the proper way to read that, but we'll go with it. This system is called a triply orthogonal system if the 3 surfaces of the system passing through any point are mutually orthogonal. The surfaces under consideration form a triply orthogonal system if and only if the vectors x sub j equal to partial x1, partial uj, partial x2, partial uj, partial x3, partial uj, where j is equal to 1, 2, or 3 respectively, satisfy the orthogonality conditions where the scalar product of x sub j with x sub k is equal to 0, where j is not equal to k, but j and k each respectively can be 1, 2, or 3. Some examples. The coordinate planes of Cartesian coordinates form a triply orthogonal system. The coordinate surfaces of the cylindrical coordinates, u1 equal to the arctangent of x2 over x1, u2 equal to the positive square root of x1 squared plus x2 squared, and u3 equal to x3, and for which we can see this depicted in figure 81 below, form a triply orthogonal system in space with the exception of the x3 axis. The same is true for polar coordinates in space, for which refer to forthcoming problem 68.2, which we will be working out. To a given one-parameter family of non-intersecting curves in a plane, there always exist orthogonal trajectories. In space, however, the analogous fact with respect to surfaces is not always true. Let an orthogonal system capital F of 2 families of surfaces be given. Then there exists a family capital G of surfaces whose surfaces intersect every surface of F orthogonally if and only if the curve of intersection of any 2 surfaces of F is a line of curvature on both surfaces. We have in fact the following. Theorem 68.1 of Dupin in 1813. The curve of intersection of any pair of surfaces of class r greater than or equal to 2 of a triply orthogonal system is a line of curvature on both surfaces. And the proof is as follows. Let capital H be a triply orthogonal system of surfaces where u1 equal to u is a constant, u2 equal to v is a constant, u3 equal to w is a constant. First refer to u1, u2, and u3 defined as the functions u, v, and w previously, satisfying the orthogonality conditions where if we have the dot product of any two of these curvilinear coordinates that are different from each other, then we get 0. It suffices to consider one of the three families of surfaces. For instance, the surfaces capital W such that the function lowercase w is equal to a constant. Since the situation with respect to the other two families where capital U corresponding to where the function lowercase u is equal to a constant and capital V where lowercase v the function is equal to a constant is the same. Lowercase u the function and lowercase v the function are curvilinear coordinates, are coordinates on the surfaces of capital W. U equal to a constant and v equal to a constant are the curves of intersection of W of the family capital W with the surfaces of capital U and capital V respectively. We have to prove that these curves of intersection are lines of curvature of the surfaces of capital W. That is, the component of the first fundamental form lowercase g sub 1, 2 is equivalent to the scalar product of x1 and x2, which is equal to 0, and the component of the second fundamental form lowercase b sub 1, 2 is equivalent to the scalar product of vector x sub 1, 2 with vector n, a normal vector, and this is equal to 0, where the indices denote partial derivatives and vector lowercase n is the unit normal vector to the surface of capital W under consideration. In consequence of the assumed orthogonality, g sub 1, 2 is equal to 0. Differentiating the orthogonality conditions scalar product statement, we obtain the following system. We have that the scalar product of x sub 1, 3 with x2 plus the scalar product of x sub 1 with x sub 2, 3 is equal to 0. Then we have the scalar product of x sub 2, 1 with x sub 3 plus the scalar product of x sub 2 with x sub 3, 1 is equal to 0. And then we have the scalar product of x sub 3, 2 with x sub 1 plus the scalar product of x sub 3 with x sub 1, 2 is equal to 0. Subtracting the first of these from the third in this system, if you will, we find that the scalar product of x sub 1, 3 with x sub 2 is equal to the scalar product of x sub 3 with x sub 1, 2. And inserting this into the second entry in this system, if you will, we have the scalar product of x sub 1, 2 with x sub 3 is equal to 0. And so when we go back to the original orthogonality conditions, then this means that x3 is orthogonal to x1 and x2, that is to the surface under consideration. To say that the scalar product of x sub 1, 2 and x sub 3 is 0 is therefore equivalent to saying that the component of the second fundamental form b sub 1, 2 is equal to 0. A theorem related to the just stated theorem of Dupin will be considered in forthcoming section 88, which is on center surfaces of a surface. Using the theorem of Dupin that we just stated, not to be confused with an earlier theorem of Dupin, we have theorem 68.2, the theorem of Louisville. The image of every sphere with respect to any admissible conformal mapping of Euclidean space is again a sphere. Here, planes have to be considered as special cases of spheres, namely spheres through the point at infinity Q. The proof is as follows. We consider an arbitrary sphere K0 with center M, and we'll prove that the image K0 star of K0 with respect to any admissible conformal mapping in space is a sphere. For this purpose, we choose a one-parameter family cursive R of concentric spheres with center M. Obviously, K0 is the surface of this family. We take a pencil cursive E of planes capital E with axis capital G through M, and a one-parameter family cursive U of coaxial circular cones capital A with axis G. So now we're at a flashback to one of the very first episodes of our differential geometry reading streams here, where I started off with that intro of Eric Weinstein gatekeeping about UAP, like you can't talk about interdimensional UAP if you don't know what a determinate line bundle and a Riemannian manifold are. And then I defined what a pencil was, like we could have a grouping of tangent lines and call that a pencil, but now we have a pencil of planes. And so we're circling back to the Wikipedia page on what a geometric pencil is. So we have A pencil of planes is the set of planes through a given straight line in 3 space called the axis of the pencil. The pencil is sometimes referred to as an axial pencil or fan of planes or a sheaf of planes. For example, the meridians of the globe are defined by the pencil of planes on the axis of Earth's rotation. Continuing on, cursive R, cursive E, and cursive U form a triply orthogonal system, cursive F naught, except on G. We denote by capital T of gamma, where gamma is greater than or equal to 0 and less than or equal to pi, a continuous rotation of the whole family cursive R, such that the axis of rotation passes through center M and an arbitrary point P naught of K naught not on G. Gamma is the angle of rotation. The families cursive E and cursive U are kept fixed. In consequence of this rotation, the curve of intersection of K naught and the plane capital E equal to capital E naught through P naught assumes every direction in the tangent plane of K naught at P naught. The rotating family cursive R equal to cursive R of gamma and the fixed families cursive E and cursive U constitute a triply orthogonal system, cursive F equal to cursive F of gamma except on G. We consider now the image cursive F star of gamma of cursive F of gamma with respect to any admissible conformal mapping. In consequence of conformality, cursive F star of gamma is a triply orthogonal system except for the image of G for every value of gamma. The continuous rotation T of gamma of K naught corresponds to a continuous motion of the image K star naught of K naught, which leaves the image P star naught of P naught fixed. In consequence of that motion, the curve of intersection of K star naught with the image of the plane E naught assumes every direction in the tangent plane of K star naught at P star naught. We conclude from Dupin's theorem 68.1 that all those curves of intersection of different directions are lines of curvature on K star naught. That is, P star naught is a navel point of K star naught. Since P naught was arbitrarily chosen, the image K star naught of K naught consists of navel points only. It is of class R star greater than or equal to 3, and thus is a sphere or a plane, for which we can refer back to theorem 48.1, which is from the section on umbilics. If every point of a surface S, which has a representation of class R greater than or equal to 3, is an umbilic, S is a plane or a sphere. And we can go back to that section, go back to that episode if we want the proof. We now come to theorem 68.3. Every admissible conformal mapping K of the space is a composition of at most 5 inversions. The proof is as follows. Let P star be the image of an arbitrary point P with respect to any admissible conformal mapping K of the space, and at the same time with respect to a suitable translation T. Then T inverse of K of P is equal to P. Let R be an inversion with pole P. By R, a plane not passing through P is transformed into a sphere K1 passing through P. T inverse K is an admissible conformal mapping. In consequence of Louisville's theorem 68.2, it maps K1 onto a sphere K2 passing through P. R transforms K2 into a plane. Hence, by the transformation A equals R T inverse KR, the arbitrary above plane is mapped onto a plane so that the image point of any point at a finite distance from the origin is a point at a finite distance from the origin. As is known, A must therefore be an affine transformation. Since A is conformal, it must be a dilatation. I think that's actually a dilation. We thus obtain K equals TRAR. Now, translation is the composition of reflections in 2 parallel planes. Reflection is inversion in the sphere of infinite radius. Dilation, I think, is the composition of inversions in 2 concentric spheres. This completes the proof. And now we have 2 problems here. Problem 68.1. Using the previously given definition for the element of arc or linear element of a curve, say capital C, denoted ds, where we can write symbolically ds squared equals the sum on the index I from 1 to 3 of dxi squared, which is equal to the scalar product of vector dx with itself, and the transformation, which is a means for introducing curvilinear coordinates, namely the function given previously, the x sub I equals function h sub I in terms of curvilinear coordinates u1, u2, and u3 for I being 1, 2, or 3 respectively. Using those, determine the linear element corresponding to arbitrary curvilinear coordinates in space. The solution is as follows. In the case of Cartesian coordinates, we have ds squared is equal to dx1 squared plus dx2 squared plus dx3 squared. Using the notation for a transformation of introducing these curvilinear coordinates, which we went over in the section, we thus obtain that ds squared is equal to a sum on the index I from 1 to 3 of the quantity partial xi partial u1 then times du1 plus partial xi partial u2 then times du2 plus partial xi partial u3 then times du3 closed quantity squared, or ds squared equal to g sub alpha beta then times du alpha du beta, where g sub alpha beta is equal to the scalar product of vector x sub alpha with vector x sub beta. Here we have to sum with respect to alpha and beta independently from 1 to 3. If the coordinates are orthogonal, then g sub alpha beta equals 0 when alpha does not equal beta for values of alpha or beta equaling 1, 2, or 3, for which we can refer back to, again, the dot product orthogonality conditions for curvilinear coordinates, and therefore ds squared is equal to g sub 1, 1, then times du1 squared plus g sub 2, 2, then times du2 squared plus g sub 3, 3, then times du3 squared. Problem 68.2. Let x1, x2, and x3 be Cartesian coordinates in space. Setting x1 equal to u1 times sine of u2, then times the cosine of u3. Setting x2 equal to u1, then times sine of u2, then times sine of u3. And setting x3 equal to u1 times the cosine of u2, we obtain spherical coordinates u1, u2, and u3. Investigate the Jacobian of this transformation and the coordinate surfaces of these coordinates. We have capital D equal to this Jacobian equal to a determinant that is 3 by 3, and we're going to go column-wise, starting with sine u2 then times cosine u3, and then sine u2 then times sine of u3, and then cosine of u2. And then in the next column, the second column, we have u1 times cosine of u2 times cosine of u3, then u1 times the cosine of u2, then times the sine of u3, and then we have negative u1 times the sine of u2. And then in the third column, entry-wise, we have negative u1 times the sine of u2 times the sine of u3, then u1 times the sine of u2, then times the cosine of u3, and then 0 to finish off this 3 by 3 determinant, which is equal to the Jacobian capital D, which is all equal then to u1 squared times the sine of u2. If u1 equals 0 or u2 equals 0, then this Jacobian capital D equals 0. That is, the Jacobian capital D vanishes at every point of the x3 axis. The orthogonality conditions of the scalar product for curvilinear coordinates equaling 0 when it's not the scalar product of the same coordinate with itself, that condition is satisfied, as can easily be verified. I believe you, I don't doubt that. We don't need to do that tediously, laboriously by hand right now. Consequently, the coordinate surfaces form a triply orthogonal system except along the x3 axis. And there you have it. We have finished reading section 68. We have finished going over the theorems, their proofs, the problems, and their solutions. And thus we have also finished reading Chapter 6 on conformal mappings in differential geometry by Erwin Kreisig. We are now at Chapter 7 on absolute differentiation and parallel displacement. We're getting to the nitty-gritty of mathematical tools from differential geometry that are directly applicable to Einstein's general relativity. See you guys in the next episode. Peace.